Okay, elc138, worksheet 19. Some of this we cannot do. One through 3 was intended to do on the trainers, but I will talk about them. Put 3 resistors in parallel, connect to a power source using the wires. Using the compass, see if you can detect a magnetic field in the wire with current flowing through it. Maybe, maybe not. There is a little compass with those trainers. Then wind the wire around a metal cylinder, which also is in there, same direction, and does the same current flowing amplify the field, in which case you should see a little greater magnetic field. If the direction of current flow is reversed, does the field reversed? So you would actually see that. So as we pass current through a wire, we create a magnetic field. If it's DC current, it's a very predictable field. It will have a definite north and a south. 4 and 5, connect the solenoid to 24 volts to see if an energized solenoid creates a magnetic field, and it certainly will. Then make it switch. Controlled normally open push button to see if it's off when the circuit is off. So what we're showing here is we're controlling the fields, the magnetic fields, strictly by passing current. Also watch the solenoid center post actuate as it is energized and de-energized. What makes the center post move in absence of a magnetic field? So when the magnetic field is off, you'll see it shift. And what's making it shift, there's actually a spring inside them that moves it out of position, and then the magnetic field brings it back. It overpowers the spring, if you will. So in order to sum up all that, is it possible to create a magnetic field without a magnet? And the answer is yes, because anytime I pass current through a wire, I will create a magnetic field. And I can enhance that magnetic field by taking that wire and winding it in a predictable fashion into a coil. So that's what you missed by not having the trainer, is seeing that. It's a pretty common effect. You should see it one day. You have to take word for it that it works. You can magnetize a screwdriver that way, wrap a wire around it, pass current through the wire, and you can magnetize a screwdriver with the DC source. Just got to be careful what you use for a source, because you don't have much resistance in the wire, and you don't want a lot of current where things will melt and get hot and you'll get injured. Okay, so that's the first 6. Millman's theorem. Solve a parallel network containing the following legs. Okay, so I'm describing the circuit here. Leg 1 is positive 12 volts with a 4.7K in series with it. Leg 2 is negative 8 volts in series with 6.2. Leg 3 is 5.6K. Leg 4 is only 11K. Okay, and so what we want to find is the voltage drops. The current in each leg, the voltage drop across the resistor in each leg, the power of the resistor in each leg. So that's what we want to find. If I go to the internet, and no, that's where I want to be. Chapter 10 of the text, Millman's theorem. Voila. So when he introduces Millman's theorem, he takes a circuit here, which is one like I like to use a lot, and he simplifies it into 3 different things in parallel. Now he's got a battery and a resistor, battery, resistor, and just a resistor. And Millman's theorem was developed because there used to not be all this great software that could analyze circuits. So let's see if we can get that just right. There we go. Brother. What if I just do that? Yay. Okay. I didn't quite make the window wide enough. Let's see if I can move that. If I do that, what's going to happen? That gets me in the window I want for sure. And now I can slide it over. There we go. And slide it down. This is what I want you to see. And if I go up just a little bit. Okay. You know the top line is just a line. So what Millman's theorem is, he's taking the voltage of each leg divided by the current of each leg. If I take a voltage and I divide it by a resistance, what do I get? I wind up with a current. Voltage over resistance equals current. So for each of the legs you have, you take the voltage in the leg, divide by the resistance in the leg, and you get a current. And you add them together. So there's two of them that have a voltage source, and the voltage source could be upside down, in which case you have to respect polarity. If this is positive polarity, then if you turn the battery around, you get negative polarity. So you've got to respect the polarity. Well, this middle leg does not have a voltage source, but the equation says it does, and what he actually plugs in is right down here. He plugs it in as a 0. So it's actually a 0 term. But for the sake of the theorem, you do it for every leg. Okay, and so you get this current, if you will, and you're going to sum up the current in each leg, and you're going to divide by the total resistance of the circuit. Now he gets that by saying, okay, all these resistors are in a sense in parallel. So he's doing the 1 over formula, but remember that is 1 over the resistance parallel. To actually get the parallel resistance, you would flip it. So what Millman's is really doing is taking a current, the total parallel currents added up, multiplying times the total parallel resistance is adding up, and you get a voltage. Okay? And this was a shortcut somebody found back when there wasn't spice to solve the problem. So if you crunch the numbers, you wind up getting 8 volts. Now the 8 volts will be the voltage between the top of the circuit and the bottom of the circuit. So if you have 8 volts here and then you have 28 volts, this 28 volts has to be reduced to 8. So you know that this 4 ohm resistor now has to drop 20 volts. This resistor drops 8 volts, and this resistor has to drop has to actually add 1 volt to it. So the voltage drop across this resistor would be such that the voltage drop from here to the bottom of the battery winds up being 8 volts. And so it just kind of works out, but when you go back to analyze it and plug in the numbers, it's a little bit different. But again, back in those days, there was no spice. So if we look at it in terms of spice, there's the circuit I described. Notice that one of my voltages is positive 12, the other one is negative 8. I've just got it flipped over. You could leave it positive and then go in and type in a negative 8. There's multiple ways to do stuff. You can flip it over. And now that you've got spice, you could do Millman's and then go in and do a dot op, and your voltage from 2 to 0, and I labeled the top wire 2 and the bottom wire with the ground is 0. Your voltage from 2 to 0 should be what you get if you properly apply Millman's theorem. Okay? It's just a shortcut to make things, circuit analysis, easier. So once you get all that, you can fill in the chart. The other part of this worksheet is triangular shaped resistances, pi or delta. And And so I'm giving you a triangular shaped resistance network containing R1 and R2 and R3, or is to be replaced by a T or a Y. Okay. Well, let's go back to the internet. Let's go back to the source. This is the delta to Y and the Y to delta conversions. Okay, so I've got my delta network, which is in the shape of a triangle. Sometimes you'll see it as a pi network, which is really the same thing. And then the Y network looks like a Y, and sometimes it'll be in the shape of a T. It's the same idea. And the way he designates his resistors is what points they're between, what nodes they're between. So if you designate in a circuit A, B, and C, and you want to replace something that looks like this with something that looks like this, then you've got to know what the equivalent is. And so he works that out down here. And the page is not big enough. So to convert to a delta, convert a delta to a Y, your RA becomes this, your RB becomes this, and your RC becomes this. Note the common denominator is the same. And then your numerator is a certain value. And this is for the first problem. If I'm converting from a Y to a delta, these are my equations. Now, you can get those equations quite easily if you go in and say, okay, if I put an ohm meter between A and B, I should get the same ohmic reading on my delta as I would get on my Y. Okay? Now, what most people miss is they think the only resistance from A to B is this resistor right here, but there's actually a parallel of 2 going around. So it's this resistor in parallel with these 2 in series would be the resistance A to B, and you would equal that to the resistance over here, which is just a RA plus RB. And if you do that for 3 different ways, I got A to C, I can measure A to C, and then I can measure from B to C and from B to C. So I can come up with all those different equations. Well, that's all he's done down here. And said that's what they're equal to with a little bit of algebra. Okay? So that would be how you would approach this problem, because triangular shaped resistance network containing R1, so it's a delta, R1, R2, and R3. So draw your delta, put in R1, R2, and R3, and you can go in and put in values 3, 5, and 4. Okay, what I typically do instead of the A, B, and stuff like he does is in my deltas I use R1, 2, and 3, and in my Ys I use RA, RB, and RC. So from a terminology standpoint, R1 is a delta resistor, R2 is a delta, R3 is a delta, and then RA, RB, and RC are my Y resistors, and that's how I normally do it. Okay, now that is not, this one's a little more tedious because you do have to use these equations and everything's different. For 14 and 15, I go in and I say, okay, based on your calculations, if the Pi delta network contained 3 6K resistances. Okay, so now my delta network has identical resistances. And what you would see is you get a simplification. And most of the time you'll see the simplification. If RA equals RB equals RC, what you wind up with is RA and RC, if they are now equal, they're the same value, or they can be used as the same term, and then these are equal. So I wind up with my resistor squared divided by 3 times that resistance. So if I subtract out that resistance, I wind up with my resistance divided by 3 would be the RA term. So with a little algebra, you see that this would reduce. And if these were all the same over here, you get a similar reduction when you're going from Y to delta. And so the second problem is a little bit easier because I'm just giving you all the same resistors. And you'll see that, hey, that one's pretty easy. For 16 through 20, what's the value of resistance? What value of resistance has a current flowing through it of 125 milliamps and a voltage drop of 16 volts? It's an Ohm's law problem. What is the voltage across the component at 4.5K resistor? Of a 4.5K resistor, if 3 milliamps is flowing through it. Another Ohm's law problem. What's the net resistance of 3 resistors in parallel? 4K, 4K, and 2K. So what's that net resistance? And what will the individual voltage drops be across 3 series resistances sourced by 10 volts if the resistors are 1K, 2K, and 3K? So now I've got a simple circuit with just 3 series resistances, because I don't want you to forget how to do all that. So those are pretty easy at the end as well. So probably the hardest one is this one. You can go in and substitute in, change my terminology to his terminology, use his formulas, or change his formulas to develop your own. It's not hidden, it's not a secret, it's there, it's just math. For the Millman's theorem, you can always do what I did, put it in LT Spice and solve it, or you can work through the actual Millman example and come up. I think you should work through the Millman example, see what you get, and then solve it in Spice to check your answers. That way you'll know they're right before you turn them in. And that is another worksheet. And good luck, and thanks for watching.